Okay, so in this video I'm going to have a look at a proof by induction for inequalities, and I'm going to prove that 3 to the power of n is greater than or equal to 2n for all n is an element of n. So for all natural numbers 1, 2, 3, 4, 5 and so on. Now as usual with these inductions, what we do is we look at 1 first of all, the first natural number here, which is 1. Put it into the left hand side, we get 3 to the power of 1, which is 3. On the right hand side we get 2 times 1, which is 2. 3 is greater than or equal to 2. So in other words, P1 is true. The proposition, in other words, P for proposition, for n is equal to 1 is true. Okay, so let's continue on then. What we need to do then is first of all make our assumption. So we're going to assume Pk is true. So in other words, we're going to assume that our proposition is true for some number k. In other words, if we take this here, we've got we have 3 to the power of k will be greater than or equal to 2k. This is our assumption then. We're going to assume that this is true. So what do we want to prove then? We want to prove that the proposition is true for the next number after k, in other words k plus 1. So this is what we want to prove. Pk plus 1 is true. In other words, 3 to the power of k plus 1 will be greater than or equal to 2 times k plus 1. This is what we want to prove. So if we can show that k plus 1 is true when k is true, then we'll be able to prove by induction that the proposition is true. I'll go through that later on anyway. So we're assuming this is true. We want to prove that k plus 1 is true. So let's have a look at this here. We have 3 to the power of k plus 1. That's just simply 3 times 3 to the power of k by our laws of indices, by our rules of indices. This is 3 to the power of 1 times 3 to the power of k. So add the powers, you get k plus 1. Now, if you look at this here, this is just really the left-hand side of our assumption here. 3 to the power of k greater than 2 to the power of 2 times k. So 3 to the power of k, we have a 3 to the power of k here, but we've multiplied it by 3. So that would mean, therefore, that if we multiply the left-hand side by 3 and multiply the right-hand side here by 3, this must be true. This here must be true because this part here we know is true from our assumption. 3 to the power of k is greater than or equal to 2k from our assumption. We want to prove this, but this here is just, this is 3 to the power of k plus 1, which is just 3 times 3 to the power of k. All I've done here really is multiply the left-hand side and the right-hand side of our assumption by 3. So this must be true. We know that this is true. So what we really need to do here, if we can show that 3 times 2k is greater than or equal to 2 times k plus 1, in other words, this is greater than this, then this thing here must be true. 3 to the power of k plus 1 must be greater than or equal to 2 times k plus 1. Another way of looking at this, just a very simplified way of looking at this, would be to say if I had a letter, let's take A, and we want to show that A is bigger than some other letter C. Now, we want to prove that this is true. So A here is really this here, 3 to the power of k plus 1, and the C is this bit over here. Now I've written this part here a different way. So I've written the A here, if you like, a different way. Still A. And I know for a fact that A happens to be bigger than, we'll say bigger than or equal to here, bigger than some other number or some other letter, and we'll call that letter B. This is our B here. I know that A is bigger than or equal to B. If I can then show that B is greater than or equal to C, then A must be greater than or equal to C. So I know this is true. If I can show that B is bigger than or equal to C, then A must be greater than or equal to C. That's effectively what I'm doing here. So I put a number in the middle here, if you like, which I know is true. I know that A is bigger than some number here. If I can show that this number in the middle here is bigger than or equal to C, then A must be greater than or equal to C. Okay, so that's what I'm going to do here. I've got to show that this is true. If I can show that this is true, then 3 to the power k plus 1 must be greater than or equal to 2 times k plus 1. So let's do that. Okay, so 3 times, I've got 3 times 2k here, and on the right hand side I've got 2k plus 2. Here I've got 6k greater than or equal to 2k plus 2. So we just do the algebra here. Let's just keep going. Bring this to, or subtract 2k from both sides, and here you get 4k greater than or equal to 2. Divide both sides by 4, and you get k greater than or equal to 2 over 4, or just k is greater than or equal to a half. Now, we know that k will always be a natural number. K will always start at 1. And go up to 2, 3, 4, 5, 6, and so on. So is k always greater than or equal to a half? Yes, it is. And by, just by working our way backwards here, all of these statements must be true. Therefore, this here must be true. This part here is true. So if this is greater than this here, then this must be greater than this here. 3 to the power k plus 1 is greater than or equal to 2 times k plus 1. So we've shown that this is true. So in other words, the proposition is true. We know the proposition is true for 1 anyway, okay? So that this is true. And we've just shown that pk plus 1 is true if pk is true. So in other words, if we have some number k and it works for k, we assume that it is true for some number k rather, then it will be true for the next number up k plus 1. Now we know it's true, it works for 1, so therefore by the fact that we've proven that it works for pk plus 1, if pk is assumed to be true, then that means p2 must be true. It must work for 2. If it works for n is equal to 2, then it must work for n is equal to 3, the next number up from 2. If it works for 3, then p4 must be true, and so on. P5 must be true, and so on and so on. So we'd say by induction, the proposition is true for all n is an element of n. And that's it.